Good morning, students. Welcome to the 12th session of lecture on Basics of Electrical and Electronics Engineering. So we'll continue our session on Unit 3, Fundamentals of AC Circuits. Today we'll discuss difference between single-phase and three-phase circuits, and also we'll study about advantages of three-phase system over single-phase system. Now, let us understand the difference between single-phase and three-phase circuits. In a single-phase system, it consists of one winding and two connecting leads or terminals. So you can see here, this is one winding. The winding has got two ends labeled as 1 and 2. So in case of a single phase system, it consists of just one winding and two connecting leads. So 1 and 2 are the two connecting leads or terminals. And in India, the single phase voltage is 230 volts. Now let us see what is a three-phase system. A three-phase system consists of three windings and two connecting ends or terminals for each winding. So you can observe here, there are three windings, winding A, winding B, and winding C. Every winding has got two connecting leads. 1 and 2 is the connecting leads of winding A, and again here this 1 and 2 is the connecting leads of B, and this 1 and 2 is the connecting leads of winding C. Each winding is called as a phase winding and is usually or normally designated as R phase, Y phase, and B phase. So for easy identification, they are connected with red, yellow, and blue wires. So R stands for red, Y for yellow, and B for blue. So when we represent a three-phase diagram, you can see as it is represented by three different colors. This can be the voltage or the current in the three different phases. So here is just a list of standard voltages which have been adopted in different countries. So for example here, Great Britain has a single phase supply of 240 volts and a three-phase supply of 415 volts and working at 50 Hertz frequency. While in America, the single phase voltage is around 115 volts and three-phase is around 230 volts at a frequency of 60 Hertz. Similarly, if you take, for example, Philippines, it has a single phase supply of 115 volts and a three-phase of 240 or 480 volts working at 60 Hertz. And in India, we have the standard voltage adopted for single phase voltage is 230 volts and for three phase it is 240 bar 415 volts at 50 Hertz frequency. 240 volts means it is the voltage between the phase and the neutral, whereas 415 volts is the voltage between two lines or two phases. Next, interconnection of three-phase system. So in a three-phase system, each phase winding has two ends. So totally there are 6 ends or terminals. But we have to bring out only 3 terminals for external connection. Hence, the 3-phase windings are interconnected to form a 3-phase, either a star system or wave system, or delta system or mesh system. So in the previous slide here, we have seen there are 3 windings here, A, B, C, where their ends have not been connected. But if we have to interconnect these ends, and finally we have to bring out only 3 terminals from that, then the connection, the way of connecting these 3 windings can be either in star, it can be connected as a star system, also called as a wave system, or it can be connected in delta system or mesh system. Now let us understand what is a star system. In a star system, you can observe here the ends of the winding. That is, one end of the winding of all the 3 windings are brought to a common point, and that point is called as the neutral, while the other ends of the coils can be connected to the external circuit. So this type of connection here, it looks like a star. You can see it looks like a star. So hence it is called as a star system. Here you can see the 3 windings. Red stands for the R phase, yellow stands for the Y phase, and blue stands for the B phase here. So R, Y, B. You can observe here the 3 windings are connected in such a way the dissimilar ends have been connected together. For example, suppose you call this end as A and the other end as A bar. Here you call it as B and this end as B dash. This is C and this end is C dash. Then the A is connected to C dash, A dash is connected to B, B dash is connected to C. So the start and finish of the windings are oppositely connected here. So such a type of connection here, which you can see is in the shape of the symbol delta. So therefore it is called as a delta system or mesh system. Now this is just for your understanding here. So the phase is usually represented by red, neutral is represented by black, and the earth is represented by green. These are universal colors which are used to represent phase, neutral, and earth. Now currently the phase is also represented by brown, the neutral is represented by blue, and the earth is represented by using the green and yellow color. Earlier, these colors were used for universally to represent phase, neutral, and earth. Now, in the present day system, even these colors are being used. That is, for phase, brown is used, for neutral, blue, and for earth, green and yellow color is being used. So here you can see how it is going to be connected. Now this is the line. Here there is the fuse which is connected to the appliance, and from the appliance is connected to the neutral wire. It is going to be connected. Now this is the plug inside the plug, this is the construction. So you can see blue is the neutral wire, yellow and green is the earth wire, and the brown one is the live wire for which the fuse is going to be connected. Now, live wire actually always carries the current to the appliance. The neutral wire completes the circuit by forming a path for the current back to the mains. It is usually at 0 volts. So when the current starts flowing from the mains, it flows through the live wire, it flows through the appliance, and again it returns back to the supply through the neutral wire. Earth wire has very low resistance and is usually connected to the metal casing of the appliances. It forms a safety outlet for the current in case the appliance becomes live. Suppose there is any fault occurring in the appliance, then to safeguard the operating personnel, the appliance is always connected to the earth so that the current does not flow through the operating personnel and he will not receive a shock. So just as a safety measure, the appliances are going to be earthed using the earth wire. Let us discuss the advantages of three-phase system over single-phase system. For the same size of a three-phase alternator has more output capacity than a single-phase alternator. So naturally, when you are using three-phase, the output capacity of the alternator is enhanced. For transmission of same amount of power, three-phase system requires less conductor material than a single-phase system. In case of three-phase system, lighting and power can be drawn from the same line, but in case of single-phase system, separate lines have to be drawn. Three-phase motors are self-starting, while single-phase motors are not self-starting. For the same output capacity, a three-phase motor is smaller in size than a single-phase motor. Three-phase motors have smooth torque, while single-phase motors have pulsating torque. Power factor and efficiency of three-phase motor is better than that of single-phase motor. And three-phase motors can be built to larger capacity, while the single-phase motors cannot be built to very large capacities. Let us move to the topic on transformers. And here we'll be talking about working principle, construction, working, voltage transformation ratio, turns ratio and current ratio, applications, and ratings. Now, what is a transformer? Transformer is a static device which transfers electrical energy from one circuit to another circuit, either at the same voltage or at a different voltage, but at the same frequency. So, it is a static device. Static device means it does not have any moving parts, and it transfers electrical energy from one circuit to another circuit, either at the same voltage or at a different voltage, but at the same frequency. So no change in the frequency. And it works on the principle of electromagnetic induction and mutual induction. So this is how a transformer is represented, symbol of a transformer. This represents the primary winding of the transformer. This is the secondary winding of the transformer. So by drawing lines here, it represents it is an iron core transformer. So here are a few pictures of transformers. So you must be familiar, you must have seen these transformers on the roadsides, you might have observed. So here it is a transformer. These are the various parts of the transformer. This is another type of transformer. So these are different types of transformers. Now, you have already studied electromagnetic induction. Now let us recall what is electromagnetic induction. It is a phenomena by which an EMF is induced in a conductor due to the change in the flux linking with the conductor. So you can carry out a simple experiment for this. Now this is a coil which is wound on an iron core, and here you have a bar magnet, and here you have a galvanometer. Whenever there is a movement in the magnet, that is, either you move the magnet towards the solenoid or you move the magnet away from the solenoid, you can observe the galvanometer shows a reading. And when you are going to move towards the solenoid, it moves in one direction. And when you are moving the bar magnet away from the solenoid, the pointer deflects in the opposite direction. And when there is no movement of the bar magnet, the galvanometer shows zero current. That is, no current is flowing in the coil. So by this, what do we understand? So electromagnetic induction is a phenomena by which an EMF is induced in a conductor due to change in the flux linking with the conductor. So when you are moving the bar magnet to and fro from the coil, there is a change in the flux linking with the conductor. Because of the change in the flux linking with the conductor, an EMF is induced, and since this is a closed circuit here, a current starts flowing in the coil, and that current is read by the galvanometer which is connected here. So this induced EMF is of different types. It can be dynamically induced EMF or statically induced EMF. And again, statically induced EMF is of two types. One is mutually induced EMF and self-induced EMF. Now let us understand clearly what is dynamically induced EMF. Now it is the EMF induced in the conductor due to the relative motion between the magnetic field and the conductor. Relative motion. Now what do we understand by this term? Relative means either you are moving the magnetic field or you are moving the conductor. Either ways, either you move the magnetic field or you move the conductor. So we'll just look here. So in this you can observe either you can move the magnetic field. In this case it is a simple bar magnet. You can move it to and fro, or you can keep the bar magnet constant and you can move the coil arrangement to and fro from the bar magnet. So this is due to the relative motion between the magnetic field and the conductor, an EMF is induced, and that EMF is called as dynamically induced EMF. Now this type of induced EMF is seen or induced in generators. Next is, what is statically induced EMF? It is the EMF induced in the conductor due to the change in the magnitude of the flux linking the conductor when both the magnetic field and the conductor are stationary. So in this case, neither the magnetic system is moving nor the conductor is moving. So there is no motion. Both of them are stationary. Both of them are not moving. But there is a change in the magnitude of the flux linking with the conductor. So an EMF induced in such a way is called as statically induced EMF, and this is the type of EMF induced in transformers. So let us again recall what is mutual induction. Whenever the flux produced by coil 1, you can observe here there are two coils. This is coil 1, this is coil 2. So across coil 1 you have connected an AC supply, and coil 2 is connected to a galvanometer. There is no electrical connection between the two coils, but the two coils are magnetically coupled. Means whenever the flux produced in coil 1 links with another coil 2, and EMF is induced in the coil 2. So here, once you are giving supply to coil 1, a current starts flowing in the coil. Now, because a current is flowing here, a magnetic field is set up around the coil. Magnetic field is nothing but magnetic lines of force, or it is also called flux. Now, this flux is linking with the coil 2. The two coils are placed close by, and once when current starts flowing in the first coil, a magnetic field is set up around that coil, and this magnetic field is linking with the second coil as shown here. Now, this induced EMF is proportional to the rate of change of flux and the number of turns on coil 2. So, whenever the flux linking here is changes, how can we change the flux linking? By varying the magnitude of the current. So whenever you are going to vary the magnitude of the current flowing in the coil, then the amount of magnetic field or flux set up around the coil is going to be varied. Thereby the flux linking with the second coil is going to vary. So, and an EMF is going to be induced in the second coil. Therefore, this induced EMF is proportional to rate of change of flux and the number of turns on coil 2. Now, this can be represented by an equation. E2 is proportional to d phi 1 by dt into N2, where E2 is the EMF induced in the secondary. Secondary means the second coil. The coil 1 can always be referred to as primary coil, that which is connected to the supply, and coil 2 is the secondary coil, that which is connected to a load. So here E2 is the EMF induced in the secondary or coil 2. N2 is the number of turns on the secondary or coil 2 in this case, and phi 1 is the flux produced by the primary and linking with the secondary. So the flux is the amount of magnetic lines of force which is set up here. So that is represented as phi 1. So here you must pay attention to the subscripting here. So E2 refers to the secondary or coil 2. Phi 1 here represents means flux set up in the primary. N2, 2 represents here number of turns on the secondary. So d phi by dt is nothing but rate of change of flux. D by dt of is the flux. So d phi by dt is nothing but rate of change of flux. Now, having understood the electromagnetic induction and mutual induction, we can understand the working of transformer better. So now transformer works on the principle of mutual induction. That is, whenever the flux produced by coil A links with another coil B, an EMF is induced in coil B. This induced EMF is proportional to the rate of change of flux and the number of turns on B, and it is given by E proportional to d phi 1 by dt into N2. So when they ask what is the principle of working of a transformer, you are expected to give an explanation about the electromagnetic induction and the mutual induction. Now, the working of a transformer. So here you can see A here is one coil which is connected to the supply E1. Let N1 be the number of turns on this coil, and this is called as the primary, which is connected to the supply. B is the second coil placed close to coil A, and N2 is the number of turns on the coil B, and the voltage across the second winding, the secondary, is E2. When an AC supply is given to coil A, that is the primary. So here you can see this is the laminated core. On this portion of laminated core is called as the leg of the transformer, leg or limb of the transformer, and the top portion, this part and this part, is referred to as the yoke of the transformer. So the winding is wound on one leg, and that which is connected to the supply is called as the primary winding, and the winding wound on another leg and that which will be connected to the load is called as the secondary winding. So when an AC supply is given to coil A here, that is the primary, AC current flows through the coil here. AC current flows through the coil and produces a changing flux phi 1. So you can see whatever is the dotted lines here, it is the flux that is set up in the core of the transformer due to the current flowing in the primary winding. Now this changing flux links with the coil B here. This is coil B or the secondary. You can see here whatever is the flux produced here is linking with the secondary. So flux produced by the primary is linking with the secondary coil or the coil B, and an EMF is induced in it. So here an EMF is going to be induced in it. How? By mutual induction. So just now we have studied the concept of mutual induction. Now let us understand the construction of the transformer. So here this is the transformer core. So as I told you, this vertical portion is called as the leg or limb, and the top portion is called as the yoke of the transformer. It has got two windings, namely primary and secondary. The primary is connected to the input circuit or the supply, and the secondary is connected to the output circuit or the load circuit. Now these two windings are placed on a laminated iron core of high permeability. The two windings here, the primary as well as the secondary, is placed on a laminated iron core. Now let us understand the meaning of laminated iron core. See, the entire transformer core is not made up of a single solid iron core. Instead, a number of stampings of the shapes E and I, this is one type of combination, and another is E and E. You can see here, this is another type of lamination. And here L, two L's, you can see two L's connected like this, or a U and a I. So a number of stampings you can see here are connected or riveted together So a number of such stampings are stacked together. Stacked means they are placed one on top of the other and bolted. Okay, you can see here, you can observe this. Bolted, you can observe the bolts, or riveted together. So this is another view here. So you can see a number of stampings here, and together it is going to form a solid block like this. So it is not a single solid core like this. Instead, a number of stampings are stacked together and they are bolted or riveted together. Now these are called as laminations. These are laminations or of thin sheets of soft iron or even silicon steel is used in the construction. Now the purpose of going in for lamination is to reduce the eddy current losses in the transformer. So now we understood here, these two windings are placed on a laminated iron core. So laminations are done in order to reduce the eddy current losses. And core of high permeability. So this is another word which you have to understand the meaning. High permeability. Now, what is permeability? The property of the material by virtue of which it allows itself to be magnetized. That is, it allows the creation of flux in itself. So it allows the existence of magnetic flux inside itself. So it is the property of a material by virtue of which it allows itself to be magnetized. A good magnetic material should have high value of permeability, and it is represented as mu, and it varies from material to material. That means the permeability of iron is different from that of steel, and that is different from copper and aluminium, like this. It varies from material to material. And mu is given by B by H. It is expressed in henries per meter, where B is the magnetic field density expressed in Weber per meter squared, and H is the magnetic field strength, which is expressed in amperes per meter. So here we'll understand here. So the two windings are placed on a laminated iron core of high permeability. Next, the complete unit is placed in a tank filled with insulating oil. So after all the winding is done, the entire unit here, what you see here, is placed in a tank filled with insulating oil. Usually mineral oil is used. The terminals of the primary and the secondary are brought out through bushings for external connection. So here are some permeability of different magnetic materials. So high permeability materials are iron, steel, nickel, cobalt, and some commercially available alloys of iron, nickel, cobalt, and other elements. Silicon steel is very popularly used in transformers. Medium permeability materials are aluminum, platinum, magnesium, chromium. Low permeability means bismuth, antimony, copper, and rare metals such as gold, silver, and mercury. And non-magnetic materials are glass, paper, rubber, wood, etc. So non-magnetic materials means they cannot be magnetized. High permeability means very easily they can be magnetized. Medium permeability means on a lesser scale, whereas low permeability, it is a bit difficult to magnetize these materials. Now, so we just now told it should have high permeability. So good magnetic materials must have high permeability. Now, how can we extend the permeability in case of a transformer? So this is just to understand the concept. So suppose you are using a coil, okay, and it is air core. That is, there is nothing in between the coils. So it is just air is going to be present. Then we call it as air core. Then the permeability is, the value is just 1. Now, suppose in the coil in between, we are going to introduce a soft iron core. That means on a soft iron core, you are going to wind the coil. Then we are going to get more inductance, and also the permeability is greatly increased, say for example, to 600. So by just introduction of this core, we have increased the permeability from a value of 1 in case of iron core to a value of 600 by using soft iron core. That means by using a core here, the magnetic field can be greatly multiplied. So here is another picture where you can see here. Now this is the air core means, see the number of lines of force. Observe the lines of force. It is lesser. That means the amount of magnetic field created around the coil is lesser. By just inserting an iron core here, you can observe here. By inserting an iron core, may give a magnetic field several hundred times that of the equivalent air core solenoid. So by just inserting this iron core, the strength of the magnetic field or is increased by several folds. It is going to be increased. So that is the purpose of using a core in a transformer. Let us continue with the construction. So we understood the construction and we came to the point that the complete unit is placed in a tank filled with insulating oil. And terminals of primary and secondary are brought out through bushings for external connection. So here is a picture. You can see the entire core. This is the transformer. This is the primary winding. This is the secondary winding. It is immersed in a tank. Here, this is the transformer tank. And you can see these are bushing terminals. That is, primary is brought out here. And this is the bushings for the secondary. So secondary terminals are is brought out here for external connections. And here the transformer tank is filled with an insulating oil. and this is the Buchholz relay, and here is the conservator tank, and this is the breather. Now this is a typical construction of an oil-filled transformer. So you can observe here, the core is placed inside the tank. These are the bushings, and Buchholz relay, conservator, and this is the breather. Excuse me. Now let us understand, just for knowledge sake, now what is the function of this Buchholz relay? Now this is a safety device which is generally used in large oil immersed transformers, which has a rating of more than 500 kilovolt amperes. It is used for protection of the transformer from the faults occurring inside the transformer, such as impulse breakdown of the insulating oil, insulation failure of the turns, etc. Conservator is when transformer is loaded and when ambient temperature rises. Ambient means the surrounding temperature is going to increase, the volume of the oil inside the transformer increases. The conservator tank provides adequate space to this expanded transformer oil. It also acts as a reservoir for the transformer insulating oil. And breather is fitted on the conservator tank, through which air is expelled or it is breathed out when the transformer is loaded, with the losses causing the oil temperature to increase and expand. During light load conditions, the oil cools down and contracts in volume, so air is breathed in from the atmosphere. So you can observe here, this is the conservator which is connected to the transformer tank, and here is the Buchholz relay. So this is a safety device. It is a safety device. It is used for the protection of transformers. So any breakdown in the oil, it immediately relays that to the nearest breaker. Now here conservator is nothing but a reservoir. It is a reservoir. You can see here, this is a reservoir. So you can observe the level of the oil here. So when the transformer is loaded, then heat is going to be produced. The oil is going to expand. So the level of the oil rises in the conservator. So when the level of the oil rises in the conservator, the air present here is going to be breathed out or expelled out through the breather. Again, during light load conditions, that is not much load on the transformer, then the temperature of the oil reduces, the oil contracts in volume, so the level of the oil is going to fall. Then air is breathed in from the surrounding atmosphere into the conservator. Next we'll come to the classification of transformers. Based on construction, it is classified as core type and shell type. Based on phase, it is classified as single phase and three phase. Based on output voltage, we have step up transformers and step down transformers. And based on service, we have power transformers and distribution transformers. And based on the cooling system adopted, we have self-cooled transformers, oil-cooled, and air-cooled transformers. So these are the different bases on which the transformers are classified. Now, based on core construction and phase, let us understand what is core type and shell type of transformers. So here you can see this is a core type. That means here this is the core of the transformer. The winding is placed on the two limbs of the transformer. As you can see, this is one limb or leg. This is another limb or leg, and windings are placed on that. So such a construction is known as core type of transformer. This is in case of single phase core type. This is how the construction is. In three phase core type, we have three limbs here. You can observe 1, 2, and 3 limbs are there on which the windings are going to be placed. So this will be the R phase, Y phase, and the B phase. Now this type of construction where the coil or the winding is placed on the core is known as the core type. So here you can see when a core type is used, when current flows through the primary winding, magnetic flux starts being set up in the laminated iron core. So that means the two windings, though they are electrically isolated, but they are magnetically coupled, and by mutual induction an EMF is induced in the secondary, and if we close this circuit, a current is flows through the secondary winding. Next, this is the shell type here. So here you can observe there is a central limb, and on the central limb the winding is going to be placed. Now this is a single phase shell type construction, whereas this is a three phase shell type construction. So on the central limb, three windings are going to be placed like this. So this is a three phase shell type construction. So this is another version here. So you can observe here, this is a central limb on which both the primary winding and the secondary winding will be placed. In core type, they are placed on different limbs, whereas in shell type, on the central limb, both primary and secondary winding is going to be placed. So here you can observe, this is the shell type where the core surrounds the winding. This is the core type where the winding surrounds the core. So here the core is surrounding the winding. Here the winding is surrounding the core. So here also you can see this is the laminations. Here this is the laminations here are 2L. This is 1L. This is the other L. And you can see here this is the core type. Here LV winding and HV winding. So the primary and the secondary are wound in layers here. And this is the shell type. The stampings used here are E and I. Laminations have been used here, and on the central limb both the LV winding and the HV. LV winding means the primary winding and HV winding is the secondary winding. So both the windings are placed on the same limb here. Now let us briefly go through the compare between core type transformer and shell type transformer. So this is the core type transformer and this is the shell type. On the two limbs, the windings are placed here. Here on the central limb, both the windings are placed. So this is shell type. So in core type transformer, winding is placed on two core limbs, whereas in shell type transformer, winding is placed on the middle arm of the core. It has one magnetic circuit or magnetic flux path, whereas in shell type, it has two magnetic circuits or magnetic flux path. So here you can see this is the flux path. There is only one path here in case of core type. Whereas in shell type, you can see this is one path and this is another path. So it has two magnetic flux path or two magnetic circuits. Next, core type transformers are used for lower voltage level applications, whereas shell type transformers are used for higher voltage level applications. Core type transformers has more leakage flux and hence more losses. Therefore, efficiency is lesser. Whereas shell type transformer has less leakage flux, hence losses are less, therefore efficiency is better. It has less mechanical protection to the coil because the coil is outward. So here there is less mechanical protection. Whereas here it has better mechanical protection to the coil because the core is surrounding the coil here. So the coils are safe inside the core. Further, transformer losses, that is copper loss and iron loss, are more in core type transformers, whereas losses are less in comparatively in shell type transformers. Repair and maintenance of core type is simpler. Repair and maintenance of shell type is a little more complex because of its construction. Here core type has two limbs and whereas shell type has got three limbs, and cylindrical windings are used in core type, whereas a sandwich type of winding is used in shell type. Sandwich means one layer is going to be primary, another layer is going to be secondary. Just like in a sandwich, one on top of the other, it is going to be placed. Natural cooling is provided since more surface is exposed to the atmosphere, whereas natural cooling is less effective in case of shell type because the winding is surrounded by the core. So it is natural cooling is less effective in compared to core type in a shell type of transformer. Next, based on output voltage, transformers are classified as step-up transformers and step-down transformers. Now, what do you mean by step-up transformer? A step-up transformer transfers electrical energy from low voltage circuit, that is primary, to high voltage circuit secondary at the same frequency. So here you can observe this is the transformer core, here is the primary winding, this is the secondary winding. Now let us say the primary winding has got 5 turns and 100 volts is applied across it, and say a current of 10 amperes is flowing through it, and let the secondary winding be of 20 turns, and the output voltage here is, let us say for example, is 400 volts and the current is 2.5 amperes at the same frequency. That is, there is no change in power. At the input also we have 1000 watts, at the output also we have 1000 watts. So at the same frequency, the voltage has been transferred from the primary side to the secondary side, but there has been an increase in the voltage. So 100 volts on the primary side has been increased to 400 volts on the secondary side. That is why it is called as a step-up transformer. So here you can see, so on the primary, low voltage, few turns and high current. So compare these two data here. On the secondary side, it has high voltage, more number of turns and low current, and secondary is connected to the load. Now this is how a step-up transformer is going to be represented. So lesser voltage is increased to higher voltage. So a low on primary and a high voltage on secondary is obtained in case of step up transformer. Now step down transformer. So the name itself tells step down. That means it is a transformer that transfers electrical energy from high voltage circuit, that is primary, to a low voltage circuit on the secondary at the same frequency. So let us look at the figure here. So you can observe here the primary has got more number of turns, say 50 turns. It is at 1000 volts. The current there is 2 amperes. Whereas the secondary has got less number of turns, that is 10 turns, and the voltage has been reduced to 200 volts, but current has increased to 10 amperes, whereas the power is same on both the input circuit, that is the primary circuit, as well as on the secondary or the output circuit. The power is the same. So here high voltage has been reduced to low voltage by using a step down transformer. So in a step down transformer, the primary has high voltage, more turns and less current, whereas the secondary has low voltage, few turns and high current. In case of a 1-to-1 ratio transformer, it transfers electrical power from the primary to the secondary circuit at the same voltage and frequency. So here both at the input and at the output, the voltage will be the same and the frequency will be the same. Now let us see what is the voltage transformation ratio, turns ratio and the current ratio. The instantaneous value of the voltage induced in the primary is given by EL is equal to N1 d phi 1 by dt volts. Similarly, instantaneous value of voltage induced in the secondary is represented by EM and is given by, because it is induced by mutual induction. So EM is equal to N2 d phi 1 by d2, where N1 is the number of turns on the primary, N2 is the number of turns on the secondary, d phi 1 by dt is the rate of change of flux linking between the primary and the secondary. Now the RMS value of voltage induced in the primary and the secondary windings are given by E1 is given by 4.445 FN1 volts, and similarly E2 is 4.445 F into N2 volts, where N1 is the number of turns on the primary, N2 is the number of turns on the secondary, phi m is the maximum flux created by the primary current, and F is the supply frequency. Now when you divide these two equations, equation 1 and equation 2, we get all these terms will cancel. 4.445 F is common in both, it cancels. What remains is E1 by E2 is equal to N1 by N2. E1 by E2 is called the voltage ratio of the transformer, and N1 by N2 is called the turns ratio of the transformer. We know that the power in a single phase transformer P in, that is on the input side, is given by E1 I1 cos phi. Similarly on the output we get P out is equal to E2 I2 cos phi. Now if the power is same, because we have just now studied, so power is transferred from primary to secondary at the same frequency. So power E1 I1 cos phi is equal to E2 I2 cos phi, and here from these two, by solving this, we get E1 by E2 is equal to I2 by I1. Cos phi gets cancelled. So if you move E2 to the denominator and this side from left hand side, I1 goes to the denominator. So we get E1 by E2 is equal to I2 by I1. This is called as the current ratio of the transformer. So in all, we can write E1 by E2 is equal to N1 by N2 is equal to I2 by I1. Now, what are the applications of the transformers? Transformers are extensively used in all AC power transmission and distribution systems to step up and step down the voltage. Step-up transformers are used in generating stations and receiving stations to step up the voltage. Step-down transformers are used in master unit substations and in distribution centers to step down the voltage. Core type transformers are used for higher capacities. Shell type of transformers are used for lower capacity requirements. Small and miniature type transformers are used in voltage stabilizers, radios, SMPS, TVs, and in laboratories and as impedance matching transformers. Instrument transformers are special type of transformers used to measure large currents and high voltages. Transformer ratings. Transformers are rated as either MVA, that is millivolt ampere, or a bigger unit is volt amperes. Even more bigger unit is kilovolt amperes, and the last one is the megavolt amperes, MVA. That's the largest rating in which it is written. The capacity of mini transformers is expressed in millivolt amperes. Small transformers are expressed in volt amperes. Capacity of power transformers are expressed in kilovolt amperes or megavolt amperes. It is the product of the rated voltage and current carrying capacity of the transformer. So here we can study, for example, what we understand by this rating. If a transformer is designed for 12 volts and 10 milliamps current carrying capacity, then its rating is given by 12 volts into 10 milliamps, that is equal to 120 millivolt amperes. So milliamps of the current, volt of the voltage is combined to give millivolt amperes. Another example, if a transformer is designed for 230 volts and 5 amps capacity, its rating is given by 230 volts into 5 amperes, that is equal to 1150 volt amperes, volt into amps. And if a transformer is designed for 110 kV and 50 ampere current carrying capacity, then the rating is given by 110 kV. kV means kilovolts into 50 amps, that is 5500 kilovolt amperes, and so on. So voltage rating of the transformer depends on the insulation provided to the transformer windings. The current carrying capacity of the transformers depends upon the size of the conductor used for the transformer windings. Now, this is very important. You have to understand why a transformer rating is in kVA and not in kilowatts. Now, transformer is a device which transfers power from one circuit to another circuit. It does not consume power. In any power consuming devices, the rating will be in kilowatts. Whereas in case of a transformer, it includes core losses and copper losses. Core losses are due to the iron core that you are using, and copper losses are due to the windings, due to the current flowing in the windings. Copper losses are also I squared R losses. So core losses is based on the input voltage, whereas copper losses is based on the current flowing through the winding. Therefore, total losses are based on voltage in addition to the current, but not on the power factor. Not on the power factor, because we know power in AC circuits, we write it as P equals VI cos phi. But here in this case, in the transformers, the cos factor is not present because it is not consuming any power here. It is not being used as a load to consume power, so we do not know the power factor. But only the voltage and the current are present, and the product of that is taken as the rating. Thus, the rating of the transformer is done in kilovolt amperes and not in kilowatts. So we know we have already studied. So this is just a summation. So transformer different types. We studied the step up transformer and the step down transformer, single phase and three phase transformers. We saw core type and shell type, and another is the instrument transformers, which are of two types: current transformers and potential transformers. And we also have power transformers and distribution transformers. So here you can see some pictures of power transformers. They are really very huge in size. Their rating is in kilovolt amperes or megavolt amperes. These are the distribution transformers here. So they are at a lesser rating of kilovolt amperes. These are instrument transformers. So these are PTs, that is the potential transformers. This is the current transformer. So this is how the transformers are placed in the yard, switching yard. This is auto transformers, which we usually use in the labs. So here you can see a variety of auto transformers. So in an auto transformer, there is only a single winding. On one side, the primary, it constitutes the primary winding, and here you can see a number of tappings. So as you rotate the knob here, you can see a knob here. So as we rotate the knob, here the value of the voltage on the secondary, different values can be obtained. So these are audio transformers, which are used for audio frequency applications, usually in the range of 20 hertz to 20 kilohertz. So you can see already how the size of the transformer has reduced when compared to the power transformers. You can see how miniature it is here in case of audio transformers. These are radio frequency transformers. So here it is in the range of 3 kilohertz to gigahertz. So high frequency, it is used in high frequency applications. Thank you. If you have any queries, you can ask.